see. Yeah, you can hear. Okay, great. Thanks. I found this new way to hide the meeting controls. I'm going to do that again. Okay. Well, welcome back, everybody. So it's the concept map of where are we. So last week we talked about how you can organize hardware in different ways with this notion of compute models. We're going to keep talking about that today. And then your reading for next week, we're moving on to something else next week, which is FPGAs versus other compute devices. So what are strengths? What are some weaknesses? So the readings are focusing on that. So lab 1 is due Monday, October 9th. And when I set this, I didn't really think about the fact that it's a long weekend. So that's Thanksgiving. What's your preference? Do you prefer like, oh, I love it. It's like it's a long weekend. I can work on it all weekend. Or you want one more day. Or you want like 3 less days. You're like, no, just move it. It's a valid option, actually. You can move it to like the Friday, and you're like, your Thanksgiving weekend is totally yours. Okay, so bring it a week forward. Okay, fair. I think I know who finished the lab early. So, okay, how many people want to, I'm going to do a really quick poll here. How many people want to leave it where it is? Okay, how many people want to move it to the Tuesday? I can give you an extra day in case you want to enjoy Thanksgiving turkey. Okay, and how many people want to move it earlier? Okay. So I mean, wants to move it earlier to make it easier to mark. Okay, I'll move it to the 10th. So I'll update the deadline after. So, but I should say, just because I'm moving it to the 10th doesn't mean you have to do it on the 10th. Sometimes people are like, you know, there's a due date for Professor Anderson's course the same week and stuff. It's like, you can do it the week before. Okay, so it's acceptable to complete an assignment before the day it's due. Okay, so readings for next week. So 2 different readings. Again, you should submit at least 10 of these, but I encourage you to do more reading because it's good for you. The first paper is from a while ago, it's 2009, but I like this paper because it very rigorously sets out to explore how efficient is a processor, just like the style of computation that a processor does, that more sequential computation, versus streaming hardware. Okay, it does them both in an FPGA. So it's basically just changing the compute model. So what can you gain or lose by changing those between those compute models? And then the second paper is one that is potentially controversial, right? In that it's doing a peak analysis. It basically says if we can use everything in a bunch of devices, GPUs, CPUs, FPGAs, all in similar process nodes, what are these guaranteed not to exceed numbers as we vary things like what kind of data types we're going to use? That's a somewhat dangerous thing to do because peak numbers are notoriously hard to achieve, but it does allow them to do an analysis across like a whole bunch of different devices that's difficult to do with just benchmarks. So you know, together this will inform some of the things we're talking about next lecture, where we're trying to get some sense of how efficient are these different basically devices. Part of your efficiency comes from what compute model you take, but another part of your efficiency comes from what kind of device are you mapping it to. So these 2 papers hopefully help inform some of that. Okay, and I'm not going to talk about this yet, so I'm going to send the projector away and do this on the Blackboard again. Okay, so let's see. Okay, so last week we were talking about basically variations of streaming models. We went from quite limited ones, but very efficient, if you could fit your computation into them, into ones that got gradually a bit more powerful. You know, being able to handle variable data rates with FIFOs and valid signals and back pressure. Being able to change the operations through either more general operators or partial reconfiguration. And we talked as we did this about some of the optimization you could do. Like again, FPGAs really like pipelining, and streaming hardware is very natural to pipeline. We talked about how retiming could fix up your pipeline some, as long as you put all the registers in the CAD tools, or you with a mechanical process can move the registers around. One last streaming optimization that comes sometimes is you can have IP blocks. So something that you didn't design, you just got it from someone. So maybe it's a hard IP block, like FPGAs have block RAMs, DSPs that can run very fast, or maybe it's an entire IP core. like an FFT. So it might be used many DSP blocks, many RAMs, lots of logic, and maybe it's really fast. Okay, so it's either hardened on the chip, so you can't really make it slower, or somebody else designed it. You can't make it slower. So you've got this fast IP block, and let's say it's a big one. So some of these IP blocks are faster than you need. They're faster than one stream. Okay, so maybe your data is coming in at, I don't know, 300 megahertz, and you're able to keep your data path going at that speed, but you have an IP core that can run at 600 megahertz. So is there anything you can do with extra with that IP core? It depends. If you have multiple streams, so if you just have one stream, there's not much, right? You just run it at 300 megahertz, and the fact that it can run at 600, it's kind of a waste, but that is what it is. But if you have a lot of streams, and again, this happens a lot in many of an FPGA's key application domains, like wireless signal processing again. You'll have many conversations, many antennas. You have a lot of data streams that you're doing signal processing on. So in that case, what you can do is you can time domain multiplex that IP block. Okay, so I want to make use of my really fast IP block because I have more work to do. The way you do that in a rigorous way is, you see, with streaming data flow, you often start tagging your data with extra information. So we put valid bits on it so we can tell when it's valid. Another thing we can do is basically here we can tag the data with a stream ID. Okay, so how does that work? So let's say I've got some function A that I wrote, and there's another function B that I also wrote, and there's streams coming into both those things. And let's say they're coming in at 200 megahertz. Okay, that's how fast I can make those blocks work. That's how fast my data naturally is arriving. Okay, so I can take those things, put them into a FIFO, and then send them into some other IP block that I didn't write. A better designer wrote those, that one, and that one runs at twice as fast. Let's say this one runs at 400 megahertz. So again, maybe these are filters, right? So it's doing some signal filtering. This is doing some more filtering. And this H is kind of expensive. So maybe it's doing filtering, maybe it's doing FFTs, but I could instantiate two copies of H, one to deal with this stream, one to deal with this stream. Okay, so these are both streams. This is like stream 0, this is stream 1. But it runs twice as fast. So what I'm going to do instead is I'm just going to have both these right into a FIFO. So this FIFO runs at 400 megahertz, so I can write into it twice as fast. I read out at 400 megahertz, or equivalently, I just write into it twice as wide. But there are multiple ways that I can send this 200 megahertz data into a FIFO and then read it out at 400 megahertz. And basically, I'll split it. So I'm going to split it based on the stream ID. So the key is that I actually have the stream ID embedded on my data. So I basically have a valid bit like I did before. I have my actual data, and I actually put an ID on it. So I tag it right on my data. It's in this case, there's just two IDs, so I just need one extra bit to tag it. That goes right into the FIFO, goes through this function, and I can use the stream ID to take it apart again. So I can figure out some of these go in FIFO A, and some go in FIFO B. Okay, so I've got it back to two separate streams. I can send it on to the downstream processing. Okay, so what I've done is I just had extra performance, and I made use of it by time domain multiplexing it. In order to make use of that, I did need to have more data to process, like independent streams. Now I could try to do something like have some state engine that said, okay, this cycle, what comes out is going to be from stream 1, and this cycle, what comes out is stream 0. A lot more robust, easier to debug, easier to reason about if you just put the ID right on your data. So you tag it. Now, no matter what the latency is through this, you just know where the data came from. Somebody goes in and repipelines this, or maybe it's got some FIFOs inside of it, so its latency isn't always the same. It's using one of those more flexible streaming style of computations. It always works out because the tag goes with the data. Let's see. Does that make sense? Yeah.
I was wondering, is there an issue with the FIFO and the expensive page going at 400 megahertz while my stream 1 and stream 0 going at 200 megahertz? Or can we just assume the FIFO can work with those two different frequencies?
Yeah, it's pretty common. Like, so all the block RAMs in FPGAs are built to have 2 clocks. Okay? You can wire both clocks to the same clock signal if you want, but we're going to see this when we get into what's inside an FPGA. Pretty much every FPGA builds RAMs that are at least dual port, and they almost always build in exactly dual port, but at least dual port. The reason is so they're good at FIFOs. Okay? So you can write in on one side, read out on the other, and they don't lock those 2 ports to the same clock frequency, for this exact reason. But it's pretty common that you have processing blocks running at different frequencies. So this can be efficiently realized in an FPGA because of the way the block RAMs are built. So that's a good question. Does that make sense? And you'll find there's actually IP in Cordis or Vivado to do this for you. It uses some block RAMs and a bit of extra logic, because there's a little bit of trickiness to the logic, like handling the full and empty flags and stuff with 2 different clocks. If you want another fun thing to do on Thanksgiving weekend, you could try to implement that logic yourself and think of all the cases. But if you prefer to eat turkey, you don't need to do this, first of all, for assignment 1. But if you prefer to eat turkey on some future occasion, you can also just use the IP cores from the vendors, which have already handled all the little tricky cases in the state machine. Does that make sense? AMD architectures actually go even further, and instead of just having block RAMs, they actually put the FIFO logic, that little bit of tricky logic is actually in hard logic right inside of it. Okay? It's not a lot of logic, so most other FPGA vendors have decided to just do it in the soft fabric, but they have IP cores so that you don't have to essentially have an exam question, right, every time you want to do this. So yeah, it's a good question. Okay, so that was time domain multiplexing. Let's see, which one of these I use. I can't move that. So there's another, time domain multiplexing turns out to be useful whenever you have independent streams of data. So I just showed you one case where it's useful. I got a streaming hardware block. It's faster than I need. Okay, could be an IP core, could be just DSP blocks and RAMs that you're using yourself. Here's another case where it's useful. So I told you loops cannot be directly pipelined. Okay, like you can't pipeline them in a mechanical way. If you put more latency in it, you got to go in and rethink all the logic. Sometimes you could do, sometimes you can't. But we can still do something about loops in a kind of mechanical way, and that's time to multiplex them. So let me use my little example here again. If I had some function f1, it was feeding a function f2. Okay, so streaming hardware blocks. I register that, and that performs my output. Okay, so this is my y value, and I'm sending in stream of inputs x, and getting out a stream of outputs y, but there's feedback. Okay. So we talked last week about how you can't just put a pipeline register in this. So if this is your critical path, that's it. You kind of got a speed limiting factor. What you can do, though, so I want to run this faster. So I really, really want to put a register here. Okay, and I can't just put it there without changing something else. There's something else that I could change. I can always do this. Is let's say I have 2 streams of data. So x1 and x2. Okay, so 2 completely separate streams of data. So again, maybe they're coming from different antennas connected to a wireless base station. Modern wireless base stations have just antennas all over the place. That's part of how and they shape the beams electrically, right? So they're scanning these beams, following you around. They got a whole bunch of them. That's part of how you're getting so much bandwidth out of wireless stations now. But it means you've got a lot of streams of independent data. So I take 2 of these, and I'm going to put them into a multiplexer and send that in. So instead of just sending 1 stream in, I can switch back and forth every cycle. Okay, so I'm going to flip this multiplexer every single cycle. And what that's going to do is basically interleave these two streams through this hardware. Okay, so let's look at what I get. Well, basically what happens is now there's 2 cycles of latency to go around this loop, whereas there used to just be 1. But I'm now separating each input from the previous one in its own stream by 2 cycles. Okay, so it matches. I put 1 extra cycle of latency in, but then I also switch between 2 different streams, and that works out. Okay, so if I were to draw out in time, what's happening is I'm getting the y1. Okay, so it's for stream 1. At time 0. Then the next output I get is actually for the other stream. So it's the y2 value for the first input. And then I'm going to go back to y1. I'm going to get the second, whoops, that should be a 1, second value for stream 1, and so on. Okay, and that just keeps going. And if I write out the equations, or I wrote out these equations that showed that if we just increased the latency of this, it was wrong, right? Like we had changed the function of the circuit. But if I write out what this does, y1 of I is exactly what we'd expect. It's f2 of f1 of x1 of I and y1 of I minus 1. Okay, so that's the exact equation I wanted, function of the current x and the previous y. And it's the same for y2, right? I'm not going to write it out, but y2 of I is equal to the same thing. I just replaced the x1 and y1 by x2 and y2. Does that make sense? I haven't proven this works, except to draw out this equation. But it's kind of intuitive. I've increased the latency around this loop, but I've increased the spacing in time between my inputs. Everything still lines up. I get the right output combined with the right input to produce the next value. Is everybody with me? So you buy it? Okay. So this actually is given a name. This is a procedure. So the general procedure is time-domain multiplexing. You can do that with any kind of hardware. You figure out that I just have a lot of independent data. You can always choose to time-domain multiplex it through your hardware. And I gave you a couple of examples of where that's beneficial. What I just did here, where I basically added another register, so you increase my clock frequency, and then I basically added another stream and multiplex between them in order to actually get a correct output, is a mechanical procedure that you can do on any streaming hardware. So it's actually given a name. It's called C-slow retiming. And the procedure is basically you make C copies of each register. Okay, so C is how much I want to, much more pipelining I want, and equivalently how many streams I'm going to multiplex between. Those two things are going to be equal. So in this case, C equals 2, right? I doubled my number of registers around this loop, and I doubled my number of streams. But it could be anything. I could have put 2 registers in here, and so change this register into, well, instead of 2 things, into 3 things, and then multiplexed across 3 streams. So that would have worked too. But the case I gave you is C equals 2. Okay, so the first thing is I make C copies of each register. Then I send in C interleaved data streams. Okay, so interleaved meaning, one sample of stream 1, then one sample of stream 2, then back to stream 1, and so on. So it's not quite what I've shown you here. So the first 2 steps would be slightly, there's one difference. I said so I'm doing 2 slow retiming. My C equals 2. So I should take this register, which is the only register I have in this design, and I should make 2 copies of it. Okay? So making 2 copies of it is actually there. So it's right beside it. that is incorrect because I increased the latency around the loop. To fix that, I put in this multiplexer so that I'm time domain multiplexing between two streams. Now it's correct again. Okay, so those are the first two steps of C-slow retiming. Is what I've done useful? What do you think? Just this. Is that a useful thing to do? Isidore saying no. Okay, so what did I do wrong? Or maybe not wrong, but why is it not useful?
It's not useful because your critical path still hasn't changed. So your F
Yeah. So it's still got this path all the way through from here to there. It's basically the same. So I added a register, I timed them in multiplexed. I still have the same clock frequency I had before, so I don't actually get any more work done. I get twice as, I get samples out at the same rate I used to get. It's just they're now from two different streams. So that's not useful. Yeah, as you're saying, maybe if there was a bunch of routing in here. Yeah, maybe the CAD tool. Well, this I actually getting at how it could be useful. So the name of this gives you a hint. Okay, so C-slow retiming. The first thing you do, duplicate every register C times. Second thing, correct it by putting in C streams. Third thing, run a retimer. Okay, now the retimer does not change the latency, but it can move around these registers. So if I run a retimer on this, it's going to go, this is fairly stupid. I want to move this register back here. So it'll erase this register and move it over here. And now I'll draw it in not dashed. And that has roughly cut my critical path in half. Does that make sense? And the retimer could move it somewhere else if these delays were such that somewhere else was better. But it'll cut your path basically in half. Okay, so the third step is you need a retimer. Okay, so what's the gain? So what do you think? Now I assert there is a gain now. Okay, after I did all these steps, what have I gained? Maybe this is too obvious. Let's kind of say. Basically, if the retiming manages to balance the delays well, which you usually can't get to extreme levels of pipelining, you can clock this about C times faster. So approximately C times faster. Okay, which means that we get C streams going through this hardware. So each of them is coming out at about the same pace they used to be. Okay, so registers are pretty cheap, unless I go completely crazy with how many. So if I did 50 slow retiming, I turned every register into 50, that's probably going to be a problem, right? It's going to stop speeding up, and that area will hurt. But here, where I just doubled all the registers, FPGAs are register rich, probably still not limited by registers. There were pretty big delays here, so I can clock this around twice as fast. I get two streams out. So if that was running at 100 megahertz, now it runs at 200 megahertz. Each stream comes out at the same rate it used to, right? So the clock frequency is twice as high, but I take two clocks to produce, between every output. But I get twice as many streams, okay? So it doesn't help my throughput of one stream or the latency of one stream, but it doesn't really hurt it either. And I do get C streams through. So as long as the hardware was more expensive than the registers, it's a pretty good optimization. Does that make sense? A few students even figure out that they can use this optimization in assignment 1. So you don't have to, but a few people figure out that they can do this on one of the compute models, not pipelined, in assignment 1. But that's not a statement that you have to do this. There's just a few people who figure out they can. Okay, so that's it for streaming hardware. And we talked a lot more about streaming hardware than I'm going to talk about most of the other models. The reason is because it's such an efficient paradigm, so widely used in FPGAs. But it's not the only thing. And most designs in an FPGA will combine multiple compute models. So it's not like you do everything in the same way. So Another one. Yeah.
For the multiplexer, wouldn't this design also increase power consumption because you're multiplexing every clock cycle in essence?
Hmm. Probably. It probably increases it some because this multiplexer is going to switch every single clock cycle. So it depends how big is this. So yes, probably it does increase power consumption some, like dynamic power consumption, because I've added some switching. If this mux is relatively small compared to what I was C-slow retiming, it's probably not a big deal, right? It's not that much compared to this. The other thing it might do is often in a data path, signals don't switch at sort of 50% of clock cycles. There's like correlation in what's happening in the data path. And by interleaving several streams, I might have broken that correlation, which means that in this hardware, it might switch more often. And that could increase my power. Whether that happens or not is kind of depends on what you're doing here. For signal processing, it doesn't tend to happen. Signal processing, you tend to have a lot of relatively random things happening anyway. Like the wireless base station tower, like the data coming in off the antenna looks pretty random. Until you like run it through all these filters and figure out, it's an emoji. So does that answer your question? On the other hand, if I get to reuse my hardware, I can go into a smaller chip, and that actually cuts my static power. Because static power is the power of just when things are sitting around leaking. And the first order thing you do to reduce static power is get fewer transistors. So if you can fit your design in a smaller device, it will leak less. So yeah.
So why the golden lights makes the circuit pipelinable?
Why does it make it pipelinable? So basically, I wanted to get an extra register in here, okay? But if I put an extra register in, I break the function because it wouldn't be taking, the current x and the previous y and computing a function of them. But if I put this multiplexer in, basically I send in a value from one stream, okay? So these streams are totally independent, okay? They're like two different antennas, say. I send in a value from one stream. It's delayed by a cycle. It's delayed by another cycle. And then I get a y value, okay? And that y value comes back and is combined. It should be combined with the next x value. So this took 2 cycles. So if I was just sending in x1 every single cycle, it's wrong because I didn't combine it with the next x cycle. But I didn't do that. I'm flipping. I didn't show the control logic here, but this logic would have to be flipping the select bit here back and forth every single cycle. So basically, I sent this in, and then I sent in one from the other stream, and then I sent the next value in from this. Okay? So it took 2 cycles to get this y value. And now I'm trying to compute this function of that old y value and my new x. And because they're 2 cycles apart, it all lines up. But I needed them to be 2 cycles apart because of the fact that I put the extra register in. Does that make sense? Okay, so I'm going to erase this. So next thing I'm going to talk about is not streaming hardware. So a different way of organizing things called finite state machine with data, or FSMD. so let's see here. Okay, so finite state machine with data path it's basically a lot like a microprocessor. It's like a customized microprocessor with hardwired control. Okay, so what does that mean? So you have a finite state machine, and I build a data path that I'm going to reuse in time. So this is a somewhat less parallel architecture. So let's say I need multiply and accumulate. I build a multiplier, I build an adder. I'm going to build a mux to control what goes in there. So let's say I might have an input from the outside world, or I might have a prior result. Okay, I'm going to do that on the other one too. So I might have an input from the outside world, or I might have a prior result. I'm not showing you where that comes from yet. The outputs I'm going to send into a mux, so I can pick either my multiply or my accumulate. And I need a register file. Okay, so this isn't one register. I'm going to put in some number of registers here. It's up to me how many registers I need. And to do more complicated computations, just like a microprocessor, I need to be able to take data from that register file, send it back through, so I can gradually build up answers. So this looks a lot like the processor data path that I showed you. The difference is instead of being controlled by a bunch of instructions that we decode and produce our control signals, we basically just built a finite state machine. Okay, and that finite state machine controls all these multiplexers. Okay, so it's got outputs for these things. It controls which register are we going to write into, which registers are we going to read from, and so on. Okay, so awful lot like a microprocessor, but different control. This is basically, well, in assignment lab 1, how many people have read lab 1? So I know at least some people have read it, okay? So it's like a test. If you're kind of like, wait a sec, what's in lab 1? All I know is that it's not on Thanksgiving, right? So, okay, in lab 1, you're actually gonna use this hardware style. So which of the compute models is gonna use this? Yeah. Yeah, so there's a shared operator one. This is a shared operator data path. We built a data path. We're gonna reuse it multiple times, but we're not gonna control it with an instruction stream because we know what we're doing is pretty repetitive. We don't need like a full set of instructions and decoder. Instead, we're just going to build a finite state machine that goes through our repetitive calculations. So this isn't as efficient generally as the streaming hardware we did before in terms of throughput, but it can be very efficient in terms of area, much like a processor. And if it's doing fairly repetitive things, this finite state machine can be quite a lot simpler than an instruction memory and a decoder that figures out all the control signals. Okay, so basically this is generally not what you want to use for your highest throughput parts of your circuit, but it is suitable for maybe rare operations where you're more concerned about minimizing area than getting the highest throughput, or maybe they're not very parallel. And one of the things we said processors were good at is, there just isn't that much parallelism. You have a whole sequence of things that you need to do, and you need to do some tests. Well, this can do that, right? There's not a lot of parallelism. We have some dependencies we can't get rid of. This can be space efficient and be a good solution for that. Okay, then there's variations on this. Okay, so program model F, I would say, is VLIW. Okay, people know what VLIW stands for? How many people know what VLIW stands for? Okay, so somebody tell me what it stands for. Somebody has their hand up. Yeah, very long instruction word. So why do they say very long instruction word? It's a processor. Okay, so it's a style of processor. The very long instruction word is that instead of having a short instruction, we're going to decode it, and it's going to tell us a few signals to control our data path, maybe a few operations. It's going to encode a lot of information about controlling our data path. Okay, it could have multiple operations. So it's kind of less work to decode, but a longer instruction. And it can have more parallelism as well, because it can encode more distinct operations in the data path that are happening. Okay, so VLIW is basically related to what I just showed, finite state machine with data path. So it's basically going to control data path with instructions. But again, kind of wider instructions that more directly control those signals in the data path. If you have, so an FSM, if you have a very simple set of repeated operations, is generally going to be smaller, clock faster, etc. But if you start getting a very complicated data path where you have a lot of control signals, that FSM might start getting big. Or if you have a lot of long operations, right? You actually have a long sequence of things that you want to do. So in those cases, it may be easier than an FSM to design, and can be more efficient too, because FSMs start getting inefficient if they get really complicated. They're not just hard to write, the logic starts getting big. So they can be better for generally wide or complex data paths. Or very long sequence of operations, right? So basically when your FSM is going to start getting pretty big, it gets kind of hard to write and can get big. Yeah?
I was just wondering, so a problem with the data path then would be like, if your data path gets really, really big, you have this FSM control unit in the middle that has to make these wires way out there.
Yeah.
So would this help with that problem?
Not directly. So I mean, I can still apply all the techniques of pipelining. So I can take this FSM, and again, it's like, depends if I have essentially loops. So I look at my computation, and if I can add latency to it, like, so I can say, yeah, I don't really need this operation to come in and be done, and then I need to test its output to decide what to do next. I just know here's a sequence of things that I should be doing. Then I can actually put a cut here and put pipeline registers. Like basically, I didn't put an edge from this register back to the FSM. Okay, now I might need that edge if I had branch conditions. Well, let's say I've got a nice happy computation where I don't have a branch condition like that. I can actually put a cut here and just put pipeline registers on this. And then I could do it again. I could put pipeline registers in a few different places. Does that make sense? And that is how I can distribute this and keep it fast. Yeah?
For the VLIW, can you distribute it by basically saying, like, instead of putting it all in one big memory, you actually have a bunch of different memories and one program counter that goes to those different memories. And now the only thing you're distributing is the program counter, and the memory itself is right near the elements that are controlled by that memory.
Yeah, and you can do that. So that makes sense. So VLIW, exactly, you're right. It doesn't, VLIW is still a pretty broad term, but you can have versions of VLIW where the instructions are pretty easy to decode, and it's pretty clear which control signals essentially are being controlled by which part of the instruction word. And in that case, what you described is exactly right. It's kind of distributing that in multiple RAMs allows you to get rid of some central state, which is more problematic. When you have central state here, like this FSM, if you want to go fast, you're going to have to start putting pipeline registers on it. So those are both good points. In an FPGA, if you have a really big RAM, usually it's, we're going to get to this later in the course, there is usually no really big RAM on chip. It gets naturally by the CAD tools chopped up into a bunch of smaller RAMs that actually physically exist. So some of that distribution of the instruction word can happen automatically. But if you're kind of thinking about it as you design your data path, you can make it easier for the CAD tools. So yeah, those are good ideas. Okay, so that's VLIW. Another related programming model is SIMD. Not exactly the same, but it's kind of the same family. Okay, so this is like acronym definition day. What does SIMD stand for? Anybody know? Who knows what SIMD stands for? Okay, lots of people. Some people know twice, right? You got both hands up. You're like, I think I'm interpreting that as a cry for help. You're like, for God's sake, don't define SIMD. But I'm guessing there's probably at least somebody here who's like quietly going, I don't know what SIMD is. So what do you think? You put both hands up. What do you think SIMD is?
Single instruction, multiple data.
Yeah, single instruction, multiple data. So basically, yeah, I'm going to do the same operation on a lot of different data elements. So it has many parallel execution units. Which VLIW can have too, right? So VLIW could be controlling a whole pile of data paths, each with their own piece of the instruction word. But SIMD says they're all the same. Okay, so we only need one instruction that's not so huge to control them all. So why do we do this? Why do we do this? What's the benefit of SIMD in general or in an FPGA design in particular? Yeah.
So in particular, like if you're doing the same operation, like with a matrix, perhaps, you don't want to actually replicate the control structure. Like you don't want to make this FSM structure, stamping it everywhere and having them all doing the same thing.
Yeah.
So you can make it once and just stamp the control signal.
Yeah. That's exactly right. Okay, so basically you share the control. Which could be instructions. That's probably the way you're used to thinking of SIMD. But it also could be an FSM. So if you find that your operations are fairly repetitive, you could make it with an FSM. But in either case, you can just say, fine, take that control unit and have it control multiple things. So let me see if I can do that. I'm going to erase this one. I'm pretty sure I'm erasing like the analysis of quicksort actually. So we talked about Tony Hoare, and I recognize this from teaching 244 years ago, and this is the complexity analysis of quicksort. So Sir Tony Hoare owns this classroom from morning to night. So okay, so let's just draw what that is. So we got a control unit, could be an FSM, could be instructions, and we're just basically broadcasting it. We've got a function unit, we've got some memory. Generally have the memory feeding the instruction unit, function units. Okay, so what I just drew there is again just finite state machine or instruction control of a data path. And what makes it SIMD is I'm just going to take this and broadcast it. So I'm going to do this over and over again. Okay, so it's more efficient if you can organize your computation this way. I've got one copy of the control. It's also easier sometimes to think about. So again, these compute models are partly ways to organize your thinking and drive you towards systems that are easier to reason about and easier to make efficient. So SIMD is easier to reason about as well as being more efficient. So an example of this from a project that one of my master's students did some years ago was a matrix optimization engine. So there's a matrix operation called LU decomposition. You factor a matrix into a lower triangular and upper triangular two submatrices. Once you do that, you can rapidly solve AX equals B equations. So it's a useful but computationally intensive thing to be able to factor a matrix this way. It's a lot of parallelism, so we implemented it on an FPGA. So we wanted to make this fast, and it fit SIMD quite well. because it fundamentally is taking like entire rows and scaling them and then adding or subtracting them to other rows in order to kind of get this structure where you get an upper triangular and a lower triangular matrix. So it fit well to SIMD from an efficiency point of view, but also in terms of thinking about it. Like in terms of writing the control, it was a lot easier to think of, I've got a whole bunch of units doing this. And in the FPGA he used, he could fit 144 of these PEs in it, and they all operated in lockstep. So each was basically responsible for a column. That wasn't big enough to do the whole matrix, but instead of doing essentially one column and going, okay, let's start eliminating, like making zeros in the rows underneath me, he just needed to do that same operation to every single column. So there's a bit of setup to figure out exactly how much to scale the entries by, but once he figured that out, he could basically have 144 of these processing elements all working in lockstep to take this piece of a row and use it to, well, essentially adjust all the rows underneath so we can get a zero. So it was a good way to think about it as well. Okay. So any questions about SIMD? And obviously you probably heard about that in processors, because these techniques are not unique, obviously, to FPGAs. They're just ways to organize hardware. Okay, this next one is kind of unique. It's soft processors. Okay, so what is a soft processor? Yeah.
When you implement the processor in the FPGA fabric.
Yeah, so it's exactly right. So you didn't go buy a Xeon or some hardened ARM processor. You built one out of the FPGA fabric, right? FPGAs can build anything out of the LUTs and block grams and so on, so we can build a processor out of it. So this is years ago, but it was at Altera. They did an analysis of the IP cores at Altera, and the most popular one was Neos, which was Altera's soft processor. And it was constantly going in more and more designs. So the first analysis they did of it, it was in 30% of the designs. They did it again a few years later. It was in 50% of designs. So soft processors are quite popular. Okay, so what do you think a soft processor is good at? Or what do you think it might be bad at? Okay, so maybe I'll give you two pieces of information that may help you, or maybe it'll distract you. You decide. Okay, so I just told you that Altera, which is now still years ago, 30% initially, then 50% of designs had a soft processor in them, so very common. There's also an interesting academic work that I saw around the same time, so maybe 10 or 12 years ago, where they took an FPGA and they put, I think like 1,500 soft processors in it and ran them all in parallel to attack some computation. I forget what the exact computation was. Probably again some kind of matrix operation, something with a lot of parallelism. So yeah, what do you think soft processors are good at? Like, it's got to give you a couple of data points. What do you think, Isidore?
Two things. I mean, first, if they contrast, to the hard processor on chip, right? That's going to be good for if you have like big, heavy computations where the actual latency matters.
Yeah, and I'll say that most FPGAs now do have a few hard processors too. Usually they're ARM. So you could use a hard processor on the same chip.
Right, with the smaller processors, like you would want to make small, usually not latency critical.
Yeah.
And you have tasks that are a lot of control that aren't running very frequently.
Okay.
For example, maybe managing, the hardware resources that you have on your chip, like for control.
Yeah, so they usually are control, low throughput. I mean, one of the terms I would use is housekeeping. Maybe that's unfair, but sometimes housekeeping, like, I got to get set up, right? Like, there's some initialization, there's some unusual states, error handling. None of that stuff's very high throughput, and I might have it in various places on my design. Maybe not just in one corner. There might be various modules that each need some initialization or some error conditions and so on. So maybe I can't just use the 1 or 2 or 4 hard processor cores that I have, but the throughput requirements are not very high. So yeah, so those are good uses.
I'd add one more thing. If you can make them very small, if you don't have to add all the overhead of all the like out of order and all the pipelining and make them super expensive, you can make very small, simple cores just to do the
Right. So these soft processors are usually parameterizable, and you can narrow the data path, strip lots of features out of them, and try to make them smaller. Okay. So can make simpler. Now we're going to talk in the next week or so about sort of what are the overheads of programmability. So the overhead of FPGA programmability is pretty high. Okay, so we'll do some analysis of that. But basically building a processor out of LUTs and registers and block RAMs is a lot less efficient than building out of gates. So, so what about this case where the person used 1,500 soft processors on an FPGA? Does it seem like a good case or not? I thought of it as I mean, so without having read the paper in great detail, I thought it was a very strange compute model because you could use hard processors, a whole bunch of them, or you could use more efficient, like streaming computations in an FPGA. But basically by trying to do all your computation with a whole bunch of general soft processors, you're kind of paying for two levels of programmability, which is expensive. You pay for the fact that the FPGA can be reprogrammed to do anything. And then if you don't specialize this processor an awful lot, you pay for the fact that the processor can also do anything. Okay, so that it's, so yeah, so you think you want to use this for its strengths. I guess one of the things is we can use it for hardware control. I guess we said for control, but you know what that can be is we could have a data path, like I showed you, of 144 big processing elements. If you have one soft processor controlling that, that's fine, right? That soft processor is maybe less efficient than a finite state machine or less efficient than a hard processor, but it just doesn't matter, right? It's just not very big compared to the size of what it's controlling. So the fact that it was, you know, it's easier to update and change the algorithm of the soft processor is probably a good choice. Yeah, Isidore?
Yeah, about that example, you have FPGA and you're stamping a bunch of soft cores. Isn't that basically just what a GPU is? A bunch of simple cores.
Yeah, I mean, a GPU does a particular case of that. So I guess I should be fair of, like when you put in another layer of programmable in an FPGA, that's often called an overlay, and we'll talk about that. And there are cases where overlays actually work pretty well. But generally, it's where the overlay doesn't have too much programmability, okay? So if you have 1,500 processor cores and each of them is pretty flexible, then I would say this is probably not a great idea, okay? If they're somehow very specific to the problem, then it might turn out to be still inefficient to answer. So I'll kind of weaken it a little bit. I did once read a paper. Okay, so I was a reviewer on a paper once. So my rule of thumb, you're going to see this in a couple of papers, but in terms of, say, area delay product, which is the opposite of efficiency, that every layer of programmability costs you around 10x. Okay, like that's not a very accurate number, right? It's not always 10x. That's why I said 10, not 9 or 6 or whatever. Like, but the cost of like a layer of programmability is pretty high. There was one paper I once reviewed where they took an FPGA and they actually used it to implement a virtual FPGA. Okay, so it means that they programmed the FPGA to be a different FPGA. Like they had routing, so they program it with and say make routing muxes, make lookup tables out of your lookup tables. But to make one lookup table in this virtual FPGA would take many lookup tables in the original FPGA. So that was their first level. So they went from, so that was their first level of programmability. They went from a real FPGA to a virtual FPGA. But that virtual FPGA essentially was, you know, had lower capacity. Let's draw it as smaller. So they have this vFPGA. And then in that vFPGA, they implemented a soft processor. So they managed to get 3 levels of programmability. From the actual, you know, transistors and wires that are doing the work, the FPGA adds a level of programmability. Then they programmed it to make another FPGA that has a different architecture, and then they used that as a soft processor. And one of my grad students, when he heard about this, he said, your review should be one word. So if you've ever seen the movie Inception, right? So every time they go one level deeper in the dream state, they get time goes 10 times slower. Which I thought I wasn't that cruel in the review, but I was like, it's not a bad analogy. But anyway, whenever you're adding another layer of programmability, think about it helps you be more productive, right? You can change your design quickly, but it does have a significant cost. So it's got to really pay for itself. Okay, so anyways, we use these though. And so basically my rule of thumb is around 10x efficiency loss, for each level of programmability. So that's fine if this is a soft processor that's just doing some control tasks or some rare tasks. Probably not fine if you're just trying to do all your computation with a huge number of soft processors. And yeah, I guess this is a foreshadowing a little bit. Like, this 10x is something that kind of shocks people. It's not just FPGAs. When you actually compare a processor to if I just directly put the computation in hardware, there's also a huge efficiency gap. So basically, if you were able to just make transistors and wires do exactly the one thing you ever wanted, it is much more efficient than all these programmable solutions, but it also basically is not economic, right? Like, nobody can afford to go off and make something that does exactly one thing with no programmability. But we still got to be judicious about how much programmability we put in. Okay. Because of these use cases, you'll usually find soft processors. Every major FPGA vendor has at least one line of soft processors. Intel has Neos, AMD has Microblaze, Microchip has RISC-V. Now some of the other companies are also starting to offer RISC-V just because it's open, so there's some momentum behind it. And the underlying architecture tends to be pretty simple. Like, they don't try to make an out-of-order superscalar processor. They'll make a fairly simple 3 or 5 stage RISC pipeline, like single issue. And the reason is that that processor is not nearly as big, and it's well suited to these kind of tasks, right? Like, it doesn't need really high throughput. It should be good enough for control. Okay, so that was soft processors, but we can also, the other thing we can do with a soft processor is we can customize it. Isidore already talked about that. We can do things to make it cheaper, narrow the data path. We can change the pipeline depth. Well, so it gives us an area speed trade-off. But we can also do more. We can augment it. Okay, so we don't have to live with a general processor that's useful for anything. So there's basically 2 ways. Well, people use this to, give you a library of high performance and lower cost processors. That's one thing to do there. But when they go to augment it and make it more tailored to an application, they do it in kind of 2 different ways. So the first way they do it, or it can be done, is with custom instructions. Okay, let's see. So let me show you what a custom instruction looks like. So most soft processors, well, there's a range, but the dominant soft processor design would be a classic 5-stage pipeline. The reason is it's quite efficient, right, in terms of like the amount of throughput it gets per unit of area. So you have a fetch, you have decode, you have your ALU ops, and you write back to your register file, which I'll just call, or you do access to memory, and then you do write back to register file, okay? Does this look familiar to people? You've all studied 5-stage pipelines in computer architecture? Okay, so kind of classic. Doesn't matter if you haven't, but this is a pretty classic design for a processor. So custom instruction, how many people know what a custom instruction is? Do you know how it changes this? Yeah, so Isidore, how does it change it?
I mean, obviously you'll have to change your decode logic, but the big thing is that you'll probably add some extra units next to the ALM, and maybe just some dedicated computation, and then you can, just run that instruction.
Yeah, that's exactly right. So the normal way that custom instructions work is you have, well, some unit that I'm going to call custom. Okay, so it does something else that the ALU is not very good at, and it basically fits right into the pipeline. So the decoder, decodes this opcode was reserved for some custom instruction. So activate some control signals, which turn on some extra hardware unit that you designed. Okay, so this is now application specific, didn't come with the processor. You put in this custom unit and assigned it one of the unused opcodes. And normally it goes basically around the ALU. Okay, so instead of having an operation that goes to the normal execution units, goes to you, and then we go do our memory access right afterwards. Okay, so how well does this work? Well, what do you think? Any thoughts on like where is this going to work well? Is it going to work badly? Where might it work well, etc. So, what do you think? Think it's going to work well? Think it's going to work well all the time? Is there some killer app that you like, or some cases where you think it's not going to work well? What do you think? Any thoughts? So you think this will be good? Okay. What do you think, Isidore?
I think you also have to consider, your compiler needs to know how to use this thing. So like most compilers that you're using aren't. So you're gonna have to be like inserting your assembly instructions yourself. It'll be difficult to use.
Yeah, you usually are going to have to put some, I guess, do one of two things. Like sometimes there are like tools that allow you to kind of take this block of code and say it's going to map to that, or more commonly, you essentially are writing some inline assembly. So you're going to pay some productivity hit to have this.
One other thing that perhaps is what you were looking for is that this thing will likely be slower than your ALU in terms of Fmax, and you could slow your entire pipeline down.
Yeah, so I guess I'll tell you what it works well for. So these are all good points. So basically what I've seen this work well for is it's useful for fine-grained operations. Okay, so what do I mean by a fine-grained op? This has been bolted right into the pipeline. So this ALU has a single cycle of latency. And yeah, it clocks at the same speed as the processor. So if the soft processor clocks at 500 megahertz, we really want this to clock at 500 megahertz. We could say, no, it takes multiple cycles of latency. So maybe it takes 3 or 5 or 10. And we could do that, right? So we could still clock everything at 500 megahertz, but say when you send something to this, it takes 10 cycles. However, when we do that, these processors do not have complicated scoreboarding logic. So an out-of-order processor can keep track of, I've got various things in flight, there are dependencies on them, better not issue this. We don't want to do that in a soft processor because, again, we're like 10x less efficient in terms of how we're building this. So if we start building this out-of-order hardware, which is known to be very expensive in hard processors, right? They can afford it. But the reason you have multi-cores is they can only go so far on the out-of-order hardware before it gets too expensive. So these don't have that kind of complicated scoreboarding logic. So generally, if this takes 10 cycles, you're going to stall your pipeline. Okay, so it's really not much better than just, maybe it's still better than slowing the clock down. But it means this fits best when the latency is not that high, right? The other thing is you have to look at how much data can I get to this. It's hooked into your pipeline, which means normally this ALU gets 2 operands from the register file. So this also will get 2 operands from the register file. I could say, no, it gets 10 operands, but if it gets 10 operands, I've got to change my whole register file. And that's expensive. To actually make my register file produce 10 operands instead of 2 is expensive, and nobody else needs it. So normally that's not allowed. You say, nope, you got 2 ports to the register file, and you fit in the same clock cycle as the ALU, or you could have multiple clock cycles, but if you're not done after one, we're going to stall the pipeline. Okay, so our opportunity for parallel overlap is somewhat limited. It still has worked well. So fine-grained operations, so one that I've seen this worked well for is CRC, or cyclic redundancy check. So in a lot of error-correcting codes and in cryptography, you take a relatively small amount of data. So you can take out of a couple of registers, here's the next bit of data that you should be encrypting, for example. And you do all sorts of shifts, XORs, lookups in local memory to basically just scramble it as much as you can. And this can actually work well for that. Okay, it's this custom instruction can have all sorts of weird control over shifters and XORs, and it can have some buried state. So you could have some memory inside here that you've loaded, and it's using that to do some lookups, and it's just scrambling the bits. And it takes a relatively small number of bits in, produces a relatively small number of bits out, so it fits in the pipeline. But there was actually quite a bit of work there. Like if you do that in the ALU, it turns into a lot of instructions. So that's where I've seen you can get pretty significant speed ups. But yeah, you have these other limitations that make it harder for many other applications to get big speed ups from this. So first, I said ports. So you're limited by the register file. Okay, so I just can't get that much data into this unit. And I usually can't let it take too long, or if it takes long, it's stalling the rest of the processor, which is acceptable, but reducing my parallelism. So stall processor for long-running ops. Okay, so I think I'll take a break here in a minute, but before I do that, I'll just ask you, okay, what is another alternative? So what else could I do to augment a processor? This is a very fine-grained approach. It's kind of elegant, actually. In some ways, it's cool. But yeah, it's kind of more limited in its applicability. What do you think?
Memory mapped I/O, you have a hardened like adjacent thing that you're going to attach to your core, and you're going to say if it writes to this address, it's actually talking to your FPGA hardware that's sitting right next to it.
Yeah, it's exactly right. Okay, so I call that the coprocessor model, but it's exactly what you just described. You basically are talking to some hardware unit through memory addresses. They don't really go to memory, but basically it's going over a bus connecting you to a more loosely coupled coprocessor. So I'm going to start drawing pictures while I give you guys a break. And the advantage of that coprocessor style is, well, basically by not being so tightly coupled, we just kind of have more freedom. I'll show you like a few ways that we can use that. Okay, thanks. So let's take a break until 5:30. And I'll use the time to clean boards. 4 processor cores. And you can make, well, you can make like thousands of soft processors. So commonly this is a soft processor that you're augmenting, but could be hard. You basically, they always have an on-chip bus that they can talk to. Okay, so the on-chip bus is just, again, more, it's built out of the programmable fabric. It's not something that, well, if this is a soft processor, this is not something that pre-existed, but we can build all of the logic to make an on-chip bus, all the routing to make an on-chip bus out of our LUTs and programmable routing and so on. Usually this is done using one of 2 standards. The most common one is the ECE standard, right, which is ARM standard that most people now use for on-chip buses. There's another one that Intel uses called Avalon, but Intel will use kind of usually now either of these. AMD always uses ECE, so it's the most common one. Okay, so it's an on-chip bus. It has address, it has data, and we can connect whatever we want to this on-chip bus. So we can connect memory to it, but we can connect anything. So we can connect a coprocessor. Okay, so this coprocessor is something else that we built in the programmable fabric. And one of the nice things we can do in this coprocessor is we can do anything we want in it. We can directly connect it to memory. So this could be on-chip memory, could also be off-chip memory, right? We can connect to a DDR controller and go off-chip. We could connect to Ethernet. We can connect to anything we want. So, okay, so what have we gotten by doing this? So it's basically more loosely coupled, and one of the things we got is more memory bandwidth. So remember I said with the custom instruction, basically had 2 ports to the register file. So we get like 2 operands a cycle. This coprocessor, it can get some operands over this on-chip bus from the microprocessor. So it basically writes to some address, and this coprocessor actually sees, oh, you're writing to this address, I should grab that data. Or I am the register that maps to that address. So we can send some data to the coprocessor that way. But where we get more bandwidth is we could do things like directly hook to as much on-chip memory or off-chip memory as we want. So we kind of break this bottleneck if we can't get too much data. We get more concurrency. Okay, why do we get more concurrency? So I mentioned that for the typical soft processor, you're going to wind up stalling the pipeline if you have a long-running soft instruction. Here, the microprocessor is just writing, to control registers inside this coprocessor, so it can say start, and it can just keep running its program, doing whatever it wants. And it can pull some other register to see when this is done, or this coprocessor could interrupt it. So we can basically take very coarse-grained operations, things that might run for thousands or millions of cycles, and the microprocessor can proceed independently of the coprocessor. So it's basically bigger potential. And finally, they don't operate in lockstep, which I guess is what I just said about concurrency. So I guess that's not so much an advantage, it's just different, right? They're more loosely coupled in this paradigm. And let's see. Does this make sense to everybody at a high level? Got it? Okay. I'm going to give you an example of where this could be useful. Okay. As an example from kind of my later years at Altera. So it was to do memory interface calibration. Okay, so this is a challenge in talking to high-speed memory like DDR. And it's a challenge, it was a challenge then, it's a challenge today. So it's kind of an interesting application. So I have a design. And so this design is my logic. It's inside an FPGA. I want to talk to external memory. FPGAs can talk to all sorts of different external memory. So DDR of various generations, you can have different widths. You can have reduced latency DRAM. You can have SRAM. You can have all sorts of different stuff. When you talk to that off-chip memory, you go through two things. You go through a controller. And normally this is an IP block that you just instantiate in your design, or sometimes it's hardened nowadays. And then that controller talks to a PHY. Okay, and then that leaves the chip. So this whole thing is inside the FPGA. And generally, this is the part you care about, right? That's your secret sauce. And this is the part you just want to work, and you want it to be fast. You want it to work well. So it's all FPGA. And what's on the other side here is one of a whole bunch of different memory standards. So there are many different variations of DDR, DDR2, 3, 4, 5, GDDR, LPDDR. Reduced latency DRAM is another kind of DDR. And then you have SRAM standards and so on that are similar. So the numbers I'm going to show you are from, the project that the numbers that were current when I was doing this at Altera. They're all a bit higher now because you can go to DDR4 and DDR5, but everything else is basically the same. So DDR3, you run each of the wires between the FPGA and the DDR chip at 1.6 gigabits per second. So pretty fast. You cannot run your design at 1.6 gigahertz. Actually, even the clocks in an FPGA won't run that fast. So no matter how good a designer you are, you're never getting to 1.6 gigahertz on any FPGA that's been designed so far. And most designers, are not going to hit 800 megahertz either, right? You're not going to get too close to this. So this is fast. The way that you communicate with the DDR is you send it two things. Okay, so you send it a DQS signal and a DQ signal. Okay, this is usually 64 bits of data, but in an FPGA it doesn't have to be, right? You could say I want to use a 32-bit data bus. You can do different things. But the most common for this standard of DDR would be that you've got a 64 bits of data moving back and forth, and you also have address bits and control bits beside it. The way this is broken down is you have 7 bits of data. Those are called DQ in DDR. Okay, so the data is changing, and it's actually changing twice per strobe. Okay, so this DQS is a strobe signal. Okay, so what's a strobe signal? It's like a clock, but a clock doesn't stop. Okay, or normally doesn't stop. You can gate it. A strobe signal is a clock that just starts and stops. That's why we call it a strobe instead of a clock. It's lower power if we only send this strobe when we're actually trying to send data to the DDR chip. Okay, so that's why it's a strobe. It's called double data rate because I'm showing you right now basically what you would have for a write. The DDR chip will latch data at both edges of this strobe. Okay, so if you think of this as a clock, you go, that's one clock cycle. In one clock cycle, you actually sent 2 pieces of data. So that's where the double data rate in DDR comes from. Now, I said this is 64 bits. This is repeated 8 times. We have 1 strobe for every 8 bits. Okay, why do we have 1 strobe for every 8 bits? This is called source synchronous communication. Okay, so source synchronous means I send some data and I send a clock beside it. And it's whoever is sending the data that sends the clock. The receiving chip, which in this case is DDR, takes that clock and just uses its edges to sample the data. So that's why it's called source synchronous. The source of the data is responsible for lining up the edges. It turns out that you can't line up a strobe reliably with 64 bits of data at these speeds. There's just too much variation between the data bits, so DDR doesn't try. It says send a strobe for every 8 bits. Does everybody make sense? This is useful to understand as well because source synchronous is one of the 2 high-speed styles of communication for off-chip. Okay, we'll talk about the other style later. Okay, so what we do is and basically DDR, the idea is you have lots of cheap DDR chips talking to a smaller number of controllers. In this case, the controller is an FPGA. So DDR tries to put more complexity in the controller, less complexity in the DDR chip. So everything in this protocol is also designed to make it easier to make a DDR chip. which also makes it harder to make a controller chip, but the standards are set by the memory manufacturers, so they don't really care, right? Also, it's more efficient. You have more memory chips than controllers, so it's a logical thing to do. Okay, so how does this work? So you send the strobe and data to memory. Okay, so when you go back to like DDR1 or even just synchronous DRAM before they did DDR, you could just send the data and send the strobe, and the memory chip could just use it, okay? And it would all work. At these speeds, it turns out there's enough variation in the I/O delays due to crosstalk, temperature variations, voltage, on-die variations, and the circuit board variation, and the memory chip variation, because these memory chips actually have pretty loose specs for how much variation they can tolerate. And the reason is to get high yields, right? You don't want to throw many memory chips out, so they have pretty loose specs about how well their I/Os match each other. When you put all that together, it turns out that it is impossible to communicate at this speed reliably by just sending this strobe and assuming it'll be properly lined up with the data. Like, it just won't work. So what has to happen is there's something called calibration. So what calibration happens when you power up your design, if your design has a memory controller in it, the controller basically is the part that understands the DDR protocol. Okay, it understands that if you do a read that actually has to be broken down into a couple of steps, a row access and then a column access. The PHY is what understands timing. It goes, okay, now that you're telling me to do a row access, I need to send a row address and get a whole bunch of data back. So this is what understands the fine level timing. This understands the overall protocol. This is digital design. This is actually kind of a high-speed, funky design. So what this PHY has to do during this calibration procedure is it has to adjust the delay of each signal until the transfer is reliable. Okay, so if you look inside the FPGA IOs that actually do the last bit of this, they have programmable delay chains, so they can actually do fine shifting of the delay of the signals going through them. Also, the clocking of this has a bunch of logic in it to be able to shift the edges that are clocking this PHY. So there's a bunch of configurability in here to be able to do fine timing adjustments on the data going out and also the data coming back in for like every single one of these DQSs and every single one of these DQs. Okay, so I'm kind of setting up the scenario to see if we can make use of one of these programming models. Okay, so the data path, again, it varies. This is where an FPGA's configurability is useful. People will talk to all sorts of different variations, but a common one would be a 64-bit wide data path. Speed at the pins is 1.6 gigahertz. Your control logic, these calibration algorithms are actually complicated. You can imagine that when you actually take all of the things you can do to the clock and all the shifting you can do to the data, and you can try to invert the phase of things and so on. And there are a lot of clocks here. Actually, this PHY in Altera's IP had 7 clocks in it. Okay, so there's a whole bunch of different clock transfers happening to go from the relatively slow fabric to these very high-speed pins. So there's a lot of different things you can play with. So the control is basically a complicated calibration algorithm. That algorithm tends to be a little bit different for every flavor of DDR and width and so on. So it's also not static. There are a lot of variations of it, and it's changing as people get more clever, and it's not published. The standard doesn't say, here's your calibration algorithm. It just says you should calibrate and this should work. So it's kept secret by all the manufacturers. Yeah?
I just want to clarify, is this PHY implemented in like soft fabric or is it implemented hardened as a periphery?
So it depends on which generation you're talking about. So what I'm talking about is up to and including the Stratix 5 generation. And it was implemented in a mix, okay? So a mix meaning you needed to have certain features in the IOs or this just was not going to work, okay? So if you didn't put enough, those features in the IOs would be like certain delay chains, the ability to choose this phase of the clock or that phase of the clock, et cetera. The ability to essentially multiply the clock by a factor of 2, things like that. And then the rest of it was soft. Does that make sense? But even the parts that are in the I/O have a lot of, they're hard, but they have a bunch of configuration bits that are controlling them. But their performance requirements are high enough that if you just tried to do them outside the I/O, you couldn't do it. Does that make sense? The line of exactly how much of this is custom is moving. So in the ARIA 10, the chip they're using for Lab 1, basically there's a hard controller and a hard PHY. Now the hard PHY still has a lot of programmability in it. It's just like kind of this special programmability. And you can bypass, if you decide that the controller doesn't do what you want, you can bypass the controller and access the PHY. Does that make sense? And that's pretty common for the most recent FPGAs, that these so many people want this that it becomes a good target for hardening. So it's a complicated calibration algorithm. Okay, so the compute architecture that we chose for this was, well, exactly what I showed there. Okay, so this is a long case study to get to that. So the architecture we chose was a microprocessor plus coprocessor. Okay. Do you think this microprocessor should be a, okay, so, I'll just tell you the answer. So this microprocessor also is a soft processor, okay? So you can have a lot of these memory interfaces. So on most FPGAs, you can have 6 or 8 of these different memory interfaces, which exceeds the number of high-performance hard processors that they have. So you wouldn't want to chew up, all or actually more than all of your high-performance microprocessors to do memory calibration. So we built this with a soft microprocessor because we basically want it, right by the memory controller when a person needs it. So the architecture that we chose was you can make your own soft processor, but usually it doesn't make sense. You can just use one that already exists. So we used Altera's soft processor, Neos. And it's only doing control. So it's configurable. We narrowed its data path. We ripped every feature out, like floating point, et cetera, that we didn't need. We used the least pipeline, lowest performance version of it. And it became pretty small. So this is down to, I think, somewhat under 1,000 LUTs because it's such a bare bones processor. And that's all we needed. So that's not zero, but in chips that have hundreds of thousands to millions of LUTs, it's an acceptable cost to have that. And then we use an on-chip bus. So in this case, it was Avalon. Nowadays, you might use ECE. And that on-chip bus connected us to some block RAM. So on-chip RAM. Okay, we're going to need that for things like the instructions for this microprocessor and also any intermediate data. But basically talking to this, if you add up the bandwidth here, to talk to this DDR at 1.6 gigahertz, 64 bits at a time, this is, I'm going to do this math in a minute. Let's see, that's 8, something like 14 gigabytes a second or so. It's way more data than this processor can move, right? It can't move anything approaching that. So we need a coprocessor to talk to the memory. So we built a write coprocessor. And a read coprocessor. Okay, and they're hanging off this Avalon bus, which basically means they just have some registers in here, and certain addresses will, read or write from these registers. That's how we're going to communicate. And they're also directly attached to DDR3. Okay, they basically hook into, they are part of this PHY, right? They hook into the PHY logic and can control it. So these coprocessors can basically handle the bandwidth that we need. Because in order to see if we're able to talk to this DDR reliably, we have to talk to it at speed. We can't just say, we'll try to really slowly talk to you. First of all, it won't even respond to that. Like, it won't work. And we wouldn't be able to get the answer we need of, is this reliable yet or not? So we need to talk to it at speed. So these coprocessors can handle the speeds we need, which in this case was 12.8 gigabytes per second. But there's a lot of logic, and logic that's going to change rapidly, so we don't want to put that decision logic inside these coprocessors. We put it inside the microprocessor. Okay, so the CPU is going to set up the tests. It's going to analyze pass-fail. And decide on the next thing. Try the next thing, etc. Okay, this worked well. So as I said, the cost of it over these processors was less than 1,000 LUTs. I forget the exact number we got it down to, but it was pretty small by stripping this all out. And these could talk at speed, so the calibration worked. I told you that this has gradually been getting hardened. Inside at least the last version of this PHY and controller that I know about, there's actually a hard NEOS in here. So this isn't just an FPGA thing. When it was decided this is so common and we are confident enough that we can actually harden it into silicon, like take some of the programmability out, they kept the NEOS processor because it works, it's a good idea. It just basically got smaller when they built it not out of LUTs, but out of gates. So it's a good way to do this in any architecture. Okay, so one of the reasons this is interesting is that this was done, so the architecture I just told you was done by the team here in Toronto, but it was not the first architecture. The DDR was very challenging, so this IP core would move around the company. So it started out in San Jose, got moved to the United Kingdom for a few years, then got moved to Toronto. Everybody taking a crack at, can we make this work better, because memory speeds keep going up and the number of standards keep proliferating. So it was challenging. So we actually had a prior implementation that was done by the UK team that actually used a different programming model or computation model. They did it all in hardware. So they didn't do this. It was basically a finite state machine, not a processor, that was directly controlling data paths that were essentially finite state machine plus data path, right? So use the FSMD computation style. So which of these do you think would work better? Probably have an idea of, because of the order I described them in. So it turns out this one works better. The all hardware one, well, let me ask another question. There's no possible way you can answer, but it's hopefully will make you appreciate the answer. How big do you think the finite state machine was to control this data path in the previous generation? So no processor. Basically, these coprocessors were mixed in with a finite state machine. It was the control. How many lines of Verilog do you think that finite state machine was? So you got to think, what's the last finite state machine you've written? Maybe you've written it for Lab 1. You can go, well, it's probably more than that, right? Like, it's like a team that did this. They should have been able to write more than Lab 1. So take a random guess, because there's absolutely no way you can know the answer to this, right? So, yeah.
It's a trick question because you can just not leave out the return characters. There's just one line.
Okay, so I mean, basically make sure that extra attention on coding style for Alex's Lab 1. So you could do, how many? 10,000 LUTs. Yeah, okay, so that's actually an area. I actually don't remember how big the area was. I do remember that the area was bigger than the whole microprocessor. So finite state machines do get bigger. It was also slower. So they had multiple problems. By doing it in a finite state machine, it was very hard. It was getting hard to change the calibration algorithm. The thing is, this algorithm changed a lot, right? Like, it's the secret sauce of how you move to higher speeds. So it never ends, right? Like, the new generation comes out. Even if you had the world's best calibration algorithm, you need to change it. So it was hard to change, hard to experiment with. So that was a big problem. Area, it was bigger. The finite state machine had gotten so big that also its critical path was becoming the speed limiting part. So they actually also, the control logic was so complicated that, and remember we talked about it's hard to pipeline control logic because you have all these loops in it. So they had time enclosure problems. So the number of lines of code was 20,000 lines of Verilog. Okay, so a 20,000 line state machine is hard to maintain, and again, it wasn't keeping up. Like it couldn't actually get a good enough calibration algorithm to calibrate at the highest speeds. Yeah, so it was 20,000 lines of Verilog. The algorithm that we put in here, which continued to evolve, it was a more complicated algorithm that works better. But basically, this was already out of gas, so you weren't going to be able to keep going with this. So 20,000 line of Verilog, and yeah, bigger than the processor, and also causing time enclosure problems. So anyway, the reason I bring this one up is like sometimes the computation model that you choose can make a really big difference. So in this particular project, this was like a key decision, right? That if we had tried to use the finite state machine controlling a data path, it would not have worked. And yeah, this is a really good use of, well, processors in general, soft processors in particular, of controlling having a tricky algorithm that's controlling a bunch of hardware. Okay, so another example, a much shorter one, is basically the slow path in packet processors. Okay, so packet processing. So I've talked a bunch about wireless communication, which is mostly signal processing. So all sorts of filtering and other things like coding, like low density parity check codes. Another big market for FPGAs is wired communication, like so packet processing. Checking if packets are malicious, forwarding packets, doing all sorts of things like that. And whenever an FPGA is involved in that, it's generally because it's fast, right? You're trying to move a lot of packets, otherwise you don't need hardware acceleration. So most packets go through an all hardware pipeline. So they go through basically some kind of streaming hardware. The hardware or fast path. But you do get some unusual packets. Okay, so unusual ones can be things like management. Okay, so management would be like, I'm trying to update your routing tables. I'm not saying send this packet, look at its header, and decide where to send it. I'm actually telling you, put this new entry in your routing table. That's much less common. But it has to happen for correctness. You can also have error conditions. So some kind of various exceptional packets, unusual things. Okay, so they're not very common. It's okay to take longer, but it's not okay to throw them away. We don't want to take them and put them into this finely tuned streaming hardware because it's going to make it bigger, right? Remember, in streaming hardware, we put more functionality in, and throughput stays the same, but we wind up with more area. So it's not a good use for things that are relatively infrequent. So we put the slow path, handle these more unusual things in software. So the hardware engine has to recognize, oh, this is of the more complicated type, just kick it over to the processor. Now, in this particular case, you could use a soft processor, but even these exceptional ones usually have enough bandwidth that it starts exceeding what a soft processor can do. So it's usually still too much for a soft microprocessor. So this is where like hard microprocessors are a good case for this. Okay, so it's one of the very good use cases for it. So for example, a bunch of the most recent high-end FPGAs will have 4-core, 1.4 gigahertz approximately. I mean, that's the number in Agilix, but the AMD ones will be similar ARM processors. Okay, so in Agilix, it's an ARM A53, so a fairly powerful ARM processor, 4 of them. You go to other FPGAs, they're reasonably similar, right? If it's a lower-end FPGA, they just scale it back a bit. And that's, yeah, those are kind of the good use cases for those ones. Okay, so let's see. Okay, the last augmented processor I talk about is a vector microprocessor. So what's a vector microprocessor? Yeah. Okay, yeah, true. It's what's another word for vectors in terms of how a processor processes them? Yeah, so it's a microprocessor with SIMD, which nowadays is most high-end processors. So you can do the same thing in an FPGA. You can go build they don't generally put hard processors that have, well, I guess ARM may always have it in, but they don't focus so much on vectors in the hard processors in an FPGA, or at least not the ARM-compatible hard processors. There was a startup that I think was acquired recently that made soft vector processors. So you can make any processor more efficient if it's moving a lot of data if you add SIMD to it. It's for the same reasons we talked about before. You amortize the control. For soft processors, it's not as popular. I mean, that people have used it. The reason it's not as popular is the reason you add vectors to a processor is you've got a lot of parallel operations. You're trying to do a lot of throughput. And in an FPGA, you have other options like streaming hardware that are generally more efficient. But this has been done. The company that, for example, commercialized this was called Vector Blocks. And I think they were acquired by Microchip. Okay, so you can do that as well. Okay, and we're almost out of, if you're going, how many programming models are there? Compute models are almost done, okay? So that's it for microprocessors. Again, I think the most compelling case in an FPGA is kind of this microprocessor that's controlling a hardware data path or microprocessor connected with a coprocessor. That's where they usually work really well. So another programming model that is interesting, probably not quite as common, is cellular automata. Okay, so what does cellular automata mean? So this basically is useful for, in particular, mathematical physics. So a lot of computations operate on a grid or a lattice. Okay, so yeah, the ones that I know best from this and that are the most common are basically two-dimensional and three-dimensional partial differential equations. Okay, so it comes up a bunch in mathematical physics. So for example, the finite difference time domain. Probably most of you have never heard of FTTD. Is that right? Who knows that acronym? All right, so I just told it to you, finite difference time domain. I did my master's degree in mathematical physics, like electromagnetic stuff. This is very common there. Basically, you've learned all sorts of calculus, vector calculus, and that's how you have Maxwell's equations or vector calculus. Civil engineering and mechanical engineering have equations that are for their systems in vector calculus. Finite difference time domain just basically means turn them back into difference equations. When you first learned calculus, you probably got shown you can take differences, and if you make the differences infinitesimally small, you get differentials. Finite difference time domain just does it in the reverse. It says, let's not do infinitesimal differentials, let's just do small. So we'll basically model, for example, for electromagnetics, we're going to define a bunch of points in space that are not too far apart, so on some grid. So I'll draw one cube of a grid. And we're going to say we have, for example, y-directed electric fields at each of these points, and maybe an x-directed magnetic field at that point. And I can do this for all three components. So I can basically take a whole geometry and just define on some discrete grid what are all the components of the electric magnetic fields. So I basically discretized Maxwell's equations in space. And then I can also discretize them in time. I'll start at t equals 0, and then I'll move to t equals a little bit, and then t equals 2 times a little bit, and so on. And I basically apply local update equations. You take all the vector calculus, you turn it into finite differences. Basically, this hx is a function of the EYs around it, and actually these E's as well, at a couple different time steps, okay? So you can take basically any partial differential equation and turn it back into finite differences and solve it this way by gridding it up in space and stepping forward in time. And that's like an introduction to something that took me 2 years to do on a master's degree, so I don't expect you to understand every detail, but hopefully you're with me of like a pretty general physics solver. Okay, so why is this interesting? It's interesting because, well, we often want to solve big physics problems. If you want to model the weather, for example, you grid up a big region into really small boxes, and if you want to predict the weather for a long time, you do a lot of time steps. And if you want that to be accurate, for increasingly more time steps, you actually have to grid up space smaller and smaller so that you capture smaller and smaller details. And it's the same for all sorts of things. If you want to model like what the radiation pattern is going to be off your cell phone antenna, you can do the same thing with different equations, right? With Maxwell's equations instead of weather equations. But what's interesting about it is it kind of fits spatial computing very nicely. You can think of both the data and the operators, like the update computations, as being distributed in space, because they really are distributed in space, right? This is a little unit cube, but if you wanted to model some antenna, you would actually, basically grid up all of space that's relevant to that antenna. Okay, so we can think of the data, and the operators all being at grid points. Okay, so data is pretty obvious. For example, would be like, what's the electric field here? And again, the operators are things like, well, take the electric field on each side of me over the last 2 time steps, and subtract one field from the other field, average that over 2 time steps. So it's local update equations. That's what I mean by an operator. Okay, so it seems natural to implement this in space. Okay, so if we implement this in space, so I basically take this 3D grid and I map it to a 2D FPGA. So some set of lookup tables, their registers would be storing this electric field, and their logic would basically be computing the next electric field by getting data from their neighbors and doing additions and subtractions. So what do you think is good about that? Is there anything good about that? Yeah, Isidore, what do you think?
Parallelism is quite trivial. It's like each location can compute at the same time.
Yeah, so it's positive is very parallel.
I think it's one thing that occurs.
Any other positives? Before you go negative, anybody got another positive? Were you going to go negative? Okay, that's fine, but we got to go positive first. So any other things you can think of? So it's very parallel, but that's not enough to say you should put this in an FPGA, because there are other things you can do for parallel. What else is good? Yeah. Yeah, so Hale. Yeah, so it's very local. So it's very local communication. Fits very nicely with this distribute the state, have many operators spread out in space. Very local communication, only local storage. Okay, so we can get very good speedups from this. Okay, so now Isidore, I'm going to go to you. You're going to rain on my parade. It seems really good. I mean, there's a company in the UK called Maxler that this was one of their big markets. They've been acquired by Grok now, so they're part of Grok, but presumably they're still doing this. They basically accelerated all sorts of computations on FPGAs, but one of the areas that they had particular success was mathematical physics. So it does work, but what are some downsides?
I mean, the one thing that comes to me is that, for any, like, you want to model some differential equation, you're likely going to need a lot of points to
Yeah.
be accurate, and each of these units are probably going to be reasonably large. They run, a lot of precision, a lot of bits for each of the numbers, and then you're going to need to stamp out a lot of them, and you're going to be limited by how much you can actually fit on the FPGA size.
Yeah, so that's a good point. Often for especially the big problems, you're going to need larger precisions, which is less friendly to FPGAs. Errors can accumulate. I didn't actually think of that. That's a good point. And then the other point is a very good one that I had thought of, which is you said, basically gets big. It gets big because the most interesting problems, like that example I gave you of like weather, they want big grids, right? You want to predict the weather in a local region over the next 2 weeks. You actually need to simulate a large area to see what's going on all around you. So it gets big for the most interesting, which are also the largest computations. And then it just won't fit. Okay, so this is like blazingly fast. You can actually map all these grid points to hardware. It's incredibly fast. On the other hand, you hit like a point where you just run out of space on the chip. You could partition across multiple chips, but basically your scalability to big grids is quite poor. And yeah.
Can you kind of get around that by basically saying this large grid, as an example, if there's actually 4 grids, here, 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 and here, and then each one locally will have like a local RAM where it swaps out, and you can time multiplex computation like that?
Yes, that is a very good idea. So that's the next thing we're going to go to. We can tweak this. So the basic way you do this is every grid point maps to actually hardware on the chip, which is incredibly fast, but also has poor scalability, right? Can't do really big problems there. So let me give you one example where this wasn't actually weather. There's a paper by Andrew DeHaan, actually one of the authors of the kind of optional textbook in this course. It's a very interesting paper. He basically did FPGA placement using an FPGA. Okay, so his example was he did FPGA placement. He only did nearest neighbor swaps. And he basically used this compute model. He said, well, the FPGA is a grid, so every every position in the FPGA I'm trying to place to, basically I'm going to make hardware that understands what netlist element is here and can communicate with its neighbors to basically decide, would we improve wire length if we swapped, right? I'll take the circuit element that you're trying to implement, and you take the one I'm trying to implement. It was blazingly fast, but the problem is he needed quite a few lookup tables in order to implement like the hardware unit that could say what is going to be placed in this spot in the FPGA I'm targeting. So it was really fast, but it was really not scalable. So basically, if he had, so he could place a 2,000 LUT circuit really quickly, but he needed a 1,000,000 LUT FPGA to do that. So yeah, it's an interesting paper, but it's not super practical because it implies you have an algorithm that can place a 1,000,000 LUT circuit, and then now you use that circuit to place a lot of really small FPGAs really fast. And the same thing happens kind of in the mathematical physics model. Okay, so there's a tweak on this, which is exactly what Isidore just said. Okay, so it's given a name. It's called folded cellular automata. And yeah, what it does is it implements a part of the lattice, so a part of the space, using local operators, working on local data. And then we basically stream data through it. So you have to send in, here's the data from the previous time step, or here's the data from your boundary, right, that I've stored previously. That goes in, do all the updates, and then you stream that out to memory and move to the next point in space. So we stream data through it. So basically, we can implement a part of the grid, and over time, what part of the grid we're simulating is essentially changing. We're streaming in new data. The operator updates are all the same always, right? Like my electric field changes based on these 4 neighbors. It's just what data I have will change over time as I stream in different parts of the grid. So you stream data through it and into some global storage, usually off-chip storage. I mean, if you had enough on-chip storage, you could use it, but usually you don't. So the positive of this is we got rid of our scalability problem. We can do bigger problems. But there's a negative, right? So yeah.
Would this be useful for like graph machine learning? Because I'm thinking of looking at
Yeah, I mean,
this is like exactly how they work.
yeah, so machine learning on FPGAs tends to use streaming a lot, right? So it is an efficient way to do it. And yeah, so you can think of them as streaming architectures, or you can think of them as grid architectures. So this, you're right. And this architecture is, like the reason I use the word stream is this starts looking, it kind of hybridizes with streaming, right? Once I have this, I've got this notion of a grid, but it basically makes me make some streaming hardware that I'm sending data through. Does that make sense? So there is a negative now to what I did. So I got a big positive, I can do bigger problems, but there's kind of an obvious negative as well. Yeah, what do you think, Isidore?
I think if you're going to like stamp out multiple copies, just to getting the data from one side to the next, you're going to have to basically totally clear it out and reload it back in. You spend lots of time moving data around.
Yeah, so basically this, yeah, we can get a lot of memory traffic. So we lost some of our local storage. This can become a bottleneck. It's what got us our scalability, but it also can now limit our speed up. And as I said, it's a lot like streaming. But you can think about this grid as an organizing principle as you make that. All right. And I think the last thing I'll say on this is, so that's kind of it, except for, I'll give you one last one. H, multi-threading. We already talked about multi-threading as in the streaming context. Multi-threading is a general technique that you can use with anything, okay? So we can use, with any style. So we talked mostly about it with streaming hardware, but we can use multi-threading as well, basically to cover latency. So that's what we did with C-slow retiming. We had a latency of a loop, so we couldn't just pipeline it. But by multi-threading it, which is what another way of thinking of C-slow retiming, what it's doing, we can tolerate that loop latency and just send multiple streams or threads into it. And the other thing that we get from it is so it covers latency and it maximizes use of expensive hardware. But we can use this with processors too, right? We don't have enough independent instructions. We can basically say, well, fine, we'll send in instructions from 2 different streams and know that they don't interact, right? So this is a key part of what GPUs do to get performance. So you can use this notion of multi-threading with anything. And yeah, so as to summarize that, we'll go back to the original reason to talk about these. With a lot of different compute models, they're intended to give you, help you organize your thoughts in order to organize your hardware. And the ones that are most limited actually usually have the most efficient hardware implementations. So if you can keep most of your computation in those, say very inflexible streaming models, that's really good. And you usually find some parts of it don't fit that well. So maybe you start using soft processors or processor plus accelerators to do that. So it's useful to know the whole toolbox, but that's the idea of this. And I'm going to quickly show you one last thing. So let's see if I can send this to the projector. I'm going to move back to slides quickly. or maybe not so quickly. Whoops. Okay, let's see. Hoping that sent it to it. Okay, it looks promising.
Accelerated in FPGA.
Like this is a physical thing. I guess we could use the heat dissipation of modern electronics to heat up the lamp faster. So that might not be the intended use of that electronics, but.
We'll put a bad FPGA next to it.
So, okay, so I think I already talked about this. These are just nice pictures. These are nicer than what I can draw. Those are the actual grid updated equations for Maxwell's equations. So all three components of the electric and magnetic fields. And if you run a finite difference time domain simulator for a while, this is actually a real output. This is called a horn antenna. It's a certain kind of antenna. And this is showing the pattern of radiation that it sends out. So that would be like a typical simulation you might do with one of these physics simulators. Okay, so we're kind of mostly talking about compute models, but kind of implicit in this is, well, what kinds of hardware can you build with those compute models? And another part of that discussion is, well, what tools would you use? So I'm just going to quickly go through what tools kind of fit different compute models. So the model of computation you choose often affects how do you describe your design. So general hardware you can write in HDL. So you can write anything in HDL. It's kind of the assembly language of FPGAs, but it's used much more than assembly language would be used for processors. It's like not the only way you describe things, but it is pretty common. You can also go one level above HDL to what's called a high-level synthesis tool. There are a lot of different high-level synthesis tools. They mostly start with some variant of C or C++ with some restrictions and some extra keywords or pragmas and map it to hardware. The key distinction of what makes something an HDL versus a high-level synthesis tool is, do you know where the clocks are? Okay, so if you know this happens in one cycle, because I put a clock here, there's a register here, and there's a register there, that's an HDL. If you don't know where the clocks are, you just say this happens, but I don't know exactly how many clocks it takes, generally that's a high-level synthesis tool, because it will choose how to allocate those to clock periods. And then beyond that, there are a lot of different entry methods. All high-level synthesis tools output, pretty much all, output Verilog or VHDL. So a lot of Verilog and VHDL is written by hand. Others are output by these higher level tools, and then it goes into the rest of the CAD flow. If you're going to use a soft processor, you will generally write the code that runs on that soft processor in C. So now some of your design is done in C. And you'll develop usually coprocessors if it's doing more than housekeeping. And those could be written in high-level synthesis, could be written in HDL. Streaming data flow, commonly done in HDL, also commonly done in high-level synthesis. And there are some domain-specific higher-level synthesis. I'll talk about one of those in a little more detail. So domain-specific means it's not just trying to take a subset of C or C++. It's really targeted at some application like signal processing. It's not very good at anything else, but it's good at that, and it uses an input format that is common in that domain. There are also a lot of, we'll talk about a couple of these later on in the course, there are also quite a few domain-specific higher level synthesis tools that are basically for deep learning, right? So another common application these days where your input might be a PyTorch or TensorFlow model. And I guess I said that. HDL is actually very good to be able to read because it's like the assembly code. But again, it's also written a lot by hand. Okay, so I guess I already told this. So your input is some untimed, for high-level synthesis, your input's some untimed algorithm description, so you don't know where the clocks are. Most common is some variation of C. Some features will be forbidden, like recursion is often forbidden, memory allocation, dynamic memory allocation is often forbidden. You can't from C or C++ figure out enough parallelism. So pretty much all high-level synthesis tools have either new keywords or pragmas. Pragmas are kind of nicer in my opinion because they'll be ignored by a normal software compiler. So you can just run it through a normal software compiler and see if it functions. But the pragmas will be interpreted by the high-level synthesis tool to get you more performant hardware. So common pragmas would say pipeline this loop or make 4 copies of this hardware that executes this loop, that kind of thing. So your output is Verilog or VHDL. Let's see. So AMD and Intel both have high-level synthesis compilers that come with their CAD flows. And they're basically C with pragmas, what I just talked about. And you make hardware blocks that you can integrate in your design, write HDL to talk to them, whatever you want. Intel and AMD also have tools that incorporate some of the technology in this. So some of the software is common. But they have SYCL and OpenCL tools. SYCL is like the C+ version. OK, so OpenCL is like the open version of CUDA. OK? So a parallel version of C that was intended initially for GPUs but can be used for other things. SYCL is the C++ version of that. So you're going to find there's a lot of alphabet soup going on here. The reason I put a slash here is you can kind of go, those two things are pretty similar. And they're intended to kind of be like CUDA but more general. Okay? What these ones do is they actually use the same technology. They'll take the hotspots in your code, the things that are called kernels, and turn them into hardware. But they'll do more than that. They will also take the rest of your code, the startup code, et cetera, and they will make that run on a processor. Usually it's a separate processor in a server, but it could be a hard processor inside of your FPGA as well. So they kind of take your system design to a little bit higher level. You're not just making the hardware now. Inside one description, you can make the hardware and the code to interface it to a control processor and to do the data transfer, which can be a pretty big productivity boost. That works well for certain applications. For some other applications, it can be hard to describe all your communication that way. OK, so a quick example of a domain-specific high-level synthesis compiler. So OK, so I talked about signal processing, a big application of FPGAs. And I'm not a signal processing communication engineer, but a lot of the design of, for example, wireless and wired communication systems is actually done in Simulink, which is like a flowcharting tool integrated with MATLAB. So you basically put in filters, modulation blocks, et cetera, Fourier transforms, send in a bunch of test data, and see if you get out what you would expect. Okay? And maybe I get the right signal-to-noise ratio. Maybe I don't. I play around with my algorithm until I'm happy with the performance of my communication system. And both Intel and AMD have tools that can do this. Okay? So Intel calls theirs DSP Builder. Xilinx called their system generator. It's been renamed to something else because both companies love to rename tools. I put it on a later slide what it's now called. But you'll find this one described in Chapter 8 of the textbook, and this one I'm going to describe right now. And don't worry about the fact that they just keep morphing the names. They're generally the same tool with some additional features and a new name. OK, so I'm not going to go through this in detail. This is an example from when I was at Altera. But it's basically a particular communication center system. So it's for a particular wireless standard, like wireless networking standard. And it's taking 2 antennas in, doing a digital up conversion. And they're just highlighting how would you do this. So basically, you enter the design. And the design is entered in a way a signal processing engineer would think of it, a flow chart of a bunch of operators. So interpolation filters, scaling, FIR filters, et cetera. Specifies a target frequency, and then just presses the button. Okay? So that's usually what domain-specific high-level synthesis means is, yeah, the front end is really targeted to the end user. And the back end is targeted also to this application domain. So this tool can make, from these block diagrams, what happens is behind each one of these blocks, which is in this Simulink signal processing toolkit, so it's a commonly used toolkit, there's a parameterized IP core that can implement that block. And the high-level synthesis tool in this case understands how to connect all those things together. So it's not useful for like arbitrary C code. You couldn't even enter that. But it is very useful for all of the blocks that are in this common signal processing toolkit. Okay, and it generates RTL and you send it through the flow. So this DSP builder tool, its input is these stream, well, basically its programming model is streaming. Its input are block diagrams, very intuitive to a signal processing engineer. And its architecture is synchronous data flow. So, one of the more limited models we talked about. It uses valid bits and has decentralized control, right? So we talked about how you can have a module just looks at whether its inputs are valid to decide whether to produce an output. So it has all of its control is distributed. It does have back pressure in certain spots, but because it can calculate how much throughput it needs everywhere, it only puts back pressure where it needs it. If it can tell that the downstream hardware will never lag the upstream hardware, it doesn't put back pressure or buffering in. So it mostly uses the just use registers, right? The synchronous data flow, not the more powerful one we talked about that put in FIFOs. It only puts that in some spots. The data path automatically gets narrower and wider, so it basically increases, not just for signal precision, but just for throughput. It'll add more functional units in parallel to keep the streams going through at full speed. And it actually, you say what clock frequency you want, and it pipelines it and retimes it until it hits that. So these systems are generally feed forward, meaning they don't have a lot of loops in them, or any loops. That means I can put cut lines all over the place. So the tool knows it can, any cut line that it puts in that block diagram, it can pipeline at that point. And the IP cores have parameterizable pipelining. So it basically keeps pipelining until it's fast enough. And because of the fact that it's using this streaming style, it knows that's correct. In Stratix 4, which is a 40 nanometer FPGA, this would hit 400 megahertz, which was beyond usually what most human designers could do with hand-tuned RTL. So for this limited domain, it works really well. And in this case, actually, there was an earlier tool that Altera built that did the opposite approach. Instead of fixing the clock frequency and changing essentially the data path width by having more or fewer parallel units and pipelining more or less, it actually tried to run different operators at different frequencies. And it wasn't as efficient. So in this case, it actually was done both ways. And the alternative of try to run operators at different frequencies didn't work as well. Let's see. It also uses that technique of sometimes some of those IP cores were faster than you needed. So it used the technique that I talked about of tagging your streams with a channel ID so you could time domain multiplex those extra fast operators and get more efficiency if you had a lot of streams. Okay, and then chapter 8 of the textbook talks about the Xilinx, now AMD equivalent of this. And yeah, so there's a lot of, so Altera has DSP builder. I think Intel still calls it DSP builder. Xilinx had system generator. AMD renamed that Vitis model composer. So there's an alphabet soup, but they all mean basically the same technology. Okay, let me go another minute longer, but I don't have much more to say. So another common design flow is you write a software plus coprocessors. The common way to do that is you write the software, then you build in C. You build the accelerators in HDL, or you ask for them from an IP core library. You could integrate them by writing the buses in HDL, but more commonly you use a system integration tool. It's kind of tedious to write HDL to implement the AXI interface and hook up things and say, okay, this memory address talks to that register. So Intel has something called Platform Designer. AMD has Vivado IP Integrator. They can automate the creation of those on-chip buses. And AMD has a cool tool, which is now part of Vitis. AMD basically took most of their software tools and called them all Vitis, which is kind of confusing. I mean, it's from a branding exercise, it's maybe good, but it means you just call everything Vitis. But they have a tool inside of there where you can actually develop a C and C++ application, profile it to find the hotspots, and then you can just mark the hotspot functions and say, use high-level synthesis to turn these into hardware. And it'll actually make the interface code to basically hook that together with your software. So that's a fast flow to get a custom coprocessor going. Okay, so those are some of the interesting tools that kind of go along with your compute model. If you're using certain compute models, you can sometimes get into a very efficient flow as well. And that can be part of part of your decision of what compute model to choose. Okay, thanks everybody. Sorry